A Gompertz curve, a Gompertz function, named after Benjamin Gompertz, is a sigmoid function. It is a type of mathematical model for a time series, where growth is slowest at the start and end of a time period. The right-hand or future value asymptote of the function is approached much more gradually by the curve than the left-hand or lower-valued asymptote. In contrast to the simple logistic function in which both asymptotes are approached by the curve symmetrically, it is a special case of the generalized logistic function. Formula: y t equals a e minus b e minus c t. Display style I t equals a mathroom e caret b mathroom e caret court, closing curly bracket, where a is an asymptote. Since lim t infinity a e minus b e minus c t equals a e 0 equals a. Display style lim underscore t 2 and d a mathroom e caret b mathroom e caret court equals a mathroom e caret 0 equals a. B, c are positive numbers. B sets the displacement along the x-axis, translates the graph to the left or right. C sets the growth rate. Y scaling. E is Euler's number. E equals 2.71828. Derivation. The function curve can be derived from a Gompertz law of mortality, which states the rate of mortality decay falls exponentially with current size. Mathematically, k r 1 y t display style k caret r propto frac 1 y t closing curly bracket closing curly bracket closing curly bracket, where r equals y single quote t y t display style r equals frac y t closing curly bracket closing curly bracket closing curly bracket is the rate of growth. K is an arbitrary constant. Example uses. Examples of uses for Gompertz curves include mobile phone uptake, where costs were initially high, so uptake was slow, followed by a period of rapid growth, followed by a slowing of uptake as saturation was reached. Population in a confined space, as birth rates first increase and then slow as resource limits are reached. Modeling of growth of tumors. Modeling market impact in finance. Growth of tumors. In the 1960s, A. K. Laird for the first time successfully used the Gompertz curve to fit data of growth of tumors. In fact, tumors are cellular populations growing in a confined space where the availability of nutrients is limited, denoting the tumor size as x t. It is useful to write the Gompertz curve as follows: x t equals k exp log x 0 k exp minus alpha t equals k x 0 k exp minus alpha t. Display style x t equals k exp left log left frac x 0 k right exp left alpha t right equals k left frac x 0 k right caret exp alpha t closing curly bracket where x 0 is the tumor size at the starting observation time. K is the carrying capacity, i.e., the maximum size that can be reached with the available nutrients. In fact, it is lim t plus infinity x t equals k. Display style lim underscore t right arrow plus and d x t equals k independently on x. 0 greater than 0. Note that, in absence of therapies etc., usually it is x 0 less than k, whereas, in presence of therapies, it may be x 0 greater than k. Alpha is a constant related to the proliferative ability of the cells. Log refers to the natural log. It is easy to verify that the dynamics of x t is governed by the Gompertz differential equation. X single quote t equals alpha log k x t display style x caret prime t equals alpha log left frac k x t right x t closing curly bracket. I.e. is of the form x single quote t equals f x t f single quote x 0 display style x caret prime t equals f left x t right x t f caret prime x leq 0, where f x is the instantaneous proliferation rate of the cellular population, whose decreasing nature is due to the competition for the nutrients due to the increase of the cellular population, similarly to the logistic growth rate. However, there is a fundamental difference. In the logistic case, the proliferation rate for small cellular population is finite. F x equals alpha 1 minus x k nu f 0 equals alpha less than plus infinity. Display style f x equals alpha left 1 left frac x k right caret nu right arrow f 0 equals alpha less than plus inf d. Whereas in the Gompertz case the proliferation rate is unbounded. Lim x 0 plus f x equals lim x 0 plus alpha log k x equals plus infinity. Display style lim underscore x right arrow 0 caret plus f x equals lim underscore x right arrow 0 caret plus alpha log left frac k x right equals plus inf d. As noticed by Steele and by Weldon, the proliferation rate of the cellular population is ultimately bounded by the cell division time. Thus, this might be an evidence that the Gompertz equation is not good to model the growth of small tumors. Moreover, more recently it has been noticed that, including the interaction with immune system, Gompertz and other laws characterized by unbounded f0 would preclude the possibility of immune surveillance. Gompertz growth and logistic growth. The Gompertz differential equation, x single quote t equals alpha log k x t display style x caret prime t equals alpha log left frac k x t right x t closing curly bracket is the limiting case of the generalized logistic differential equation. X single quote t equals alpha nu 1 minus x t k 1 nu x t display style x caret prime t equals alpha nu left 1 left frac x t k right caret frac 1 nu right x t closing curly bracket, where nu greater than 0 display style nu greater than 0 is a positive real number, since lim nu plus infinity nu 1 minus x 1 slash nu equals minus log x. Display style lim underscore new right arrow plus and d new left 1x caret 1 new right equals log left x right closing curly bracket. In addition, there is an inflection point in the graph of the generalized logistic function when x t equals new plus 1 new k. Display style x t equals left frac new plus 1 right caret new k and 1 in the graph of the Gompertz function when x t equals k e equals k lim new plus infinity new plus 1 new. Display style x t equals frac k e equals k c dot lim underscore new right arrow plus and d left frac new plus 1 right caret new. Gompertz's law of growth. Based on the above considerations, Weldon proposed a mathematical model of tumor growth called the Gompertz model that slightly modifies the Gompertz law. In the Gompertz model, it is assumed that initially there is no competition for resources, so that the cellular population expands following the exponential law. However, there is a critical size threshold, x c, display style x underscore c, such that for x greater than x c, display style x greater than x underscore c, the growth follows the Gompertz law. F x equals max a alpha log k x. Display style f x equals max left a alpha log left frac k x right closing curly bracket, so that x c equals k exp minus a alpha display style x underscore c equals k exp left frac a alpha right closing curly bracket. Here there are some numerical estimates for x c display style x underscore c x c approximately equals 10 9 display style x underscore c approx 10 caret 9 for human tumors. X c approximately equals 10 6 display style x underscore c approx 10 caret 6 for murine mouse tumors. See also Gompertz distribution, growth curve, Weisstein, Eric W. Gompertz curve, MathWorld.